Okay, so I'm going to speak about these spectral results for Dirac-Coulomb operators. So in the last days and in the last workshop, we have listened to many people speaking about how to deal with systems with thousands or millions of particles, etc., etc. And I'm going to speak actually about systems with one particle. Well, you are going to see the fact that we are going to deal with relativistic atoms makes that they are even linear problems that are not easy to understand rigorously and to compute rigorously and well. So, I don't have to talk too much. I lost it. Yeah, okay. So I'm going to speak about two sets of results. At the beginning, I will speak about things that I did with Dolbeau and Séré at the beginning of around 2000. And I explain that because it's the beginning of our work on this problem, and I will describe the kind of tools that we developed there. And then I will speak about more recent results, very recent results, actually, with Mathieu Lewin and Eric Séré. So even if this problem that I'm going to speak about is a linear problem, actually it is related and it came to us working on nonlinear problems. We were working at the time with Eric Séré on Dirac-Fock equations, and we saw that one of the bricks in the method that we were developing to deal with Dirac-Fock equations was to understand the linear or the linearized problems that were related to those Dirac-Fock equations. And when we looked at that problem, we said, okay, let's see what can we say about the spectrum of these Dirac operators. And then we just started to look at the literature. As we will see later, many of you know, this is a problem which you have to find eigenvalues in gaps of the spectral gaps. So we looked in the literature. In math, we don't find anything really clear about how to deal with that, how to describe eigenvalues in gaps, how to compute them. There were many results about you can find eigenvalues, yeah, but how to really compute them. And we looked at the physics and chemistry literature, and what we found, especially in chemistry, many algorithms that people were proposing to compute eigenvalues of Dirac operators, and there were many articles because the algorithms they were proposing had problems. They had problems with convergence, they had problems with appearance of spurious roots, many of those. And so in order to avoid those problems, they were proposing particular relations between the upper, you will see afterwards, the upper and the lower spinor, which is called kinetic balance and these kind of things. And so they were proposing recipes to deal with the problems, but none of the recipes was really final. It worked for one kind of molecules, but not for the other ones, etc., etc. So we saw that both in chemistry and in math, there was not a clear answer about how to compute eigenvalues of Dirac operators. Okay, so in order to explain the problem, let me start very quickly presenting the Dirac operator. So the Dirac operator is a first-order operator. You see that you have here first derivatives. Schrödinger operator has second derivatives in it. And it has constant coefficients that in this case are the alphas and the betas. And these alphas and beta are 4x4 matrices. And I chose the units that are called the atomic units in which I get rid of all the constants, because in what I'm going to say, the value of the constants is not important. So I place myself, I choose the units in which I can say that C, the speed of light, M, the mass of the electron, H bar, Planck's constant are equal to 1. Okay, I choose atomic units, and so I can write the Dirac operator like this. And the alphas and betas are these matrices. Beta is a diagonal matrix. Here I write it in 2x2 blocks. So this is the 2x2 identity minus identity. And the alpha k's are anti-diagonal. And in the anti-diagonal, you find the very well-known Pauli matrices. Okay, the two main properties of the Dirac operator are that when you take the square, it's equal to minus Laplacian plus 1. So when you take the square, it's a positive operator. And then in Fourier, it's very easy to see from that when you look at the spectrum of the free Dirac operator, you are going to find like the eigenvalues of both square roots, because here we could take the positive and the negative formally, a little bit formally, the positive and the negative square roots. So it's very easy in Fourier variables that the spectrum of the Dirac operator is the union of two intervals, unbounded, both of them, one from minus infinity to minus 1, and one from 1 to plus infinity. Okay, so we have a spectral gap between minus 1 and 1, which plays a very important role in which I will be telling you later. And also a last remark is that since the coefficients of the operator are matrices 4 by 4, the functions on which the operator acts are functions with 4 components that are called 4 spinors, psi, which go from the physical space R3 into C4. Okay, so what is the difference between working with the Schrödinger operator and the Dirac operator? The difference is that here you see the case, for example, of the Dirac operator of the Schrödinger minus Laplacian plus a potential. So you look at the minus Laplacian, this is a non-negative operator. It has essentially a spectrum from 0 to plus infinity. But if you perturb it by, for example, negative eigenvalue, an attractive potential, you will see that you can generate eigenvalues to the left of the essential spectrum. The first one will correspond to the ground state. Then you have the other ones that correspond to the excited states of the electron. But if you are working with the Dirac operator and you also add some potential, some electrostatic potential, you will be able to generate eigenvalues in the gap. But these eigenvalues in the gap, they have a spectrum to the left and to the right. And this creates many questions. Raises many questions. Even Dirac started to, I am not going to go into that, but even when he proposed his operator, he had to explain what it meant to have negative energies, etc., etc. So, for example, one of the important questions is, well, will the first one will be the ground state? But the first one is not a minimum of anything, because the minimum of the spectrum is minus infinity. So one has to be able to compute these eigenvalues in the gap and to give a meaning to those eigenvalues, okay? So, for example, just very quickly, if you are in this case, in the case of the Schrödinger semi-bounded operator or a matrix, how do you compute the first eigenvalue? What you do is you look at the Rayleigh quotient of the operator. You take the minimum over all vectors that are different from 0, and that, if that exists, gives you the first eigenvalue, this one here, which is interpreted in quantum mechanics as the ground state energy. Okay? And the other ones will be excited states that you can find by easy min-maxes that we know, where in the max we put orthogonality with respect to the previous eigenvalues, etc., etc. Okay. But these min-maxes that we define the second, the third eigenvalues, etc., are of a type that is easy to deal with mathematically and numerically, because in some sense, when you are computing, for example, the third one you have to compute it, you have to write a min-max. But for the max, you will have orthogonality with respect to the two first ones. So you have a finite space of two-dimensional spaces to which you have to be orthogonal. But here in this situation, it's much more dramatic, because every eigenvalue, the first, the second, the third, all of them will have to, they have to be orthogonal to all the things that are below them, and that's infinite dimensional. So that means that if you pretend to say that the first eigenvalue in this gap, the one that you think in some sense will be the ground state of this relativistic electron, is a min-max, because formally it has to be a min-max. From a variational theory, mathematically, it has to be a min-max. The question is, what do you put in under the min and the max? And that was not clear when we started working with this at the end of the 90s. Not clear at all. There was no result in mathematics to know how to deal with this. And not only about Dirac, about any operator with gaps. Okay, so we understood that we should try to find a definition for this, but what? Okay, so this is what I'm going to explain. So, being mathematicians, we were talking actually at the time with some chemists, and we understood that for them what they wanted is a good algorithm. That was the only thing they wanted, and we understood very well. But in order to tell them something, we needed to understand this problem from forgetting about electrons, forgetting about Dirac, forgetting about anything. We have an operator, we have a gap in the spectrum. How do we manage to characterize the eigenvalues in that gap, and maybe to produce from that an algorithm to compute the eigenvalues, okay? But we have to understand the structure, and this is the work we do in mathematics. You have to go to a very abstract situation to understand what you have to do. So I'm going to start with a theorem that for non-mathematicians here, you are going to think that this is crazy, but it is what we have to do, and in the end, we will use that to produce a really good algorithm. So this is the theorem. Very quickly, I will go through it. So to deal with this situation, we published that in 2000. So we are in the situation in which H is a Hilbert space. We have an operator which is self-adjoint with domain included in the Hilbert space. We took at the time, now we know how to do it in an easier way, but well, at the time, we took F to be a core. What does it mean to be a core? It means to be a subset of the domain, which is dense in the domain for its topology. And then we suppose that we have two infinite dimensional spaces, H plus, H minus, that we can use to write the full space as the direct sum of the H plus and H minus. You could think, for example, if we were thinking, it's a possibility that we are not going to use, but you could think that this H plus and H minus correspond to positronic states and electronic states, for example, for the Dirac operator. It's not necessarily that, but okay. So you have the decomposition of the space as direct sum of two spaces, and then you define F plus and minus, which is P plus minus F, where P plus minus are the projections corresponding to this decomposition. Okay. Now, once we have this functional situation, we look at the Rayleigh quotient now, Ax minus Ak minus, divided by the norm of x minus a square, over all the functions that are in F minus, okay, in this negative part, if you want. And we make the assumption that this number is finite. Okay, this is the first thing. And then we define these numbers, these min-maxes, Ck, which are infimum, supremo of the Rayleigh quotient. And what we chose to put there is here we put under the inf the subspaces of F plus with dimension k. And this is the supremum of V, this V, with the whole space F minus. So this is infinite dimensional space. Okay, this looks very much like the min-maxes you use to compute eigenvalues of matrices or of semi-bounded operators. But here the situation is very difficult, very, very different, because this space is infinite dimensional. So this is absolutely not the theory of min-maxes that you can find, for example, in the book of Courant and Hilbert. Nothing at all. So actually, I could give you examples for which these numbers are not eigenvalues of the operator A, okay? So there is no reason, but it was a good guess. But we have to add an assumption, and the assumption we have to add is the following. We have to add that the first number in this series of numbers, the first one, is larger than the A minus that was defined here. If we have a gap between this C1 and this A minus, then these CKs are all the eigenvalues of A in the interval A minus B, where B is the next point in the essential spectrum. So if we are in a gap, this characterization will give us all the eigenvalues in the gap. But we have to have this assumption and this assumption. And so you have a particular operator with gap. You have to put yourself in the functional situation. You have to look at this decomposition. You have to measure these numbers, etc., etc. In any case, okay, we proved this theorem. This was a theorem. Okay, so from the mathematical point of view, you are happy. You have your theorem proved. But what do you do with it? At the time, let me just say that there were related results of Griesemer and Siedentop using not very different method to do the same thing. And recently, there has been a very interesting paper of Schimmer, Solovey, and Tokus, 2019, reviewing all these questions, okay, and changing a little bit the functional setup. Okay, so once you have that, so you see that here that you have to have a space, you have to have a decomposition, you have to have a core, and then you have to look at these numbers. Okay, so now let's come back to Dirac. So suppose that we have Dirac, and we perturbed it by a potential that is, for example, like an atomic potential. You see a potential that goes to 0 at infinity and is between is attractive, is negative, and is larger than minus nu over modulus of x. It's a Coulomb potential. Yeah. And yes?
Sorry to interrupt. Can you go back to the definition of B?
Of what?
The The small b is the infimum of the?
No, this is a different b. This is a subspace. Would be. B is the next point in the essential spectrum. So it's the infimum of the essential spectrum, which is above A minus. You have a gap, is the right part of the gap. Okay, so let's suppose that for simplicity that we take an atomic potential, and nu has to be, for reasons that we will see later, nu has to be between 0 and 1. And you could tell me, well, if nu is between 0 and 1, what kind of atom do you have? Well, you have good atoms because we are in atomic units. So nu being between 0 and 1 means that the nuclear charge is between 0 and 137. Okay? So you cover all the periodic table with this kind of potentials. Okay. So now we have to decide the decomposition that we take in the space. And the decomposition we use is something that we were inspired of a work by Talman, who, if I am not mistaken, is a Canadian chemist. And so we propose to decompose any vector with 4 components, phi and chi. So phi is the upper part of the spinor, chi is the second part of the spinor, and we decompose it as the sum of phi 0 plus 0 chi. Okay? This is a very simple. The composition is clearly orthogonal because you multiply it by this, that you get 0. So it's a very, very, very simple decomposition, and we are going to work with it. Okay, so we can verify that with this decomposition and this assumption on V, we can verify the 2 assumptions of the theorem. That's easy, it's not difficult. So we do it, okay, and then we apply the theorem to this situation. And then we see that the eigenvalues of Dirac perturbed by such a potential is given by an inf soup. Well, I write it in a horrible way just to tell you that this is really, okay, it's a theorem, but what can you do with that? Not much, okay? So we are not going to convince any physicist or chemist that our theorem is useful with this. So we try to go to a real algorithm. And so first thing we observed is that we applied our result to describe the first eigenvalue of Dirac plus V in the gap. We see a formula which is nicer. We see that it's an inf soup of the Rayleigh quotient, okay? But the inf and the soup is interesting. We take the inf with respect to the upper part of the spinor, and we take the soup with respect to the lower part of the spinor. So this is a simple formula, but if you want to compute this numerically, it's going to be very tough, because this is a saddle point with infinite dimensions going up and down, because the space of chi is infinite dimensional, and the space of phi also. So you have a saddle point, which is infinitely unstable. So approaching that numerically is going to be very, very difficult, okay? So this formula is nice, it's simple, but you want to really construct an algorithm from this, it will be difficult to approach this point. But we observed that if we look at the blue part, at this supremum over phi, so over chi, so we fix phi, the upper part of the spinor, and you look at the supremum of the Rayleigh quotient with respect to all the lower part. And we saw that this number, that is, supremum in infinite dimensional space, etc., is actually a number that is very simple to compute. Why? Because we showed that it is, this number, this supremum, is the unique lambda such that you satisfies this scalar equation. So you give me phi, V is the potential, we have the Pauli matrices, whatever here, and we have, in this equation, we have only one unknown. The unknown is the lambda, here and here. And there is a unique solution for this scalar equation. Why? Because in the left-hand side, you have an increasing function, straight line, which is increasing. And in this part, you have that this is decreasing. Because V I took, for example, an attractive potential, so minus V is positive. Everything is positive here. So this function is decreasing in lambda, and this is increasing in lambda. So you are looking at the crossing of an increasing and a decreasing function, and you can see that there is unique solution, lambda, for this. Okay? So this is something that you can really compute numerically very easily, because you have, you're right, I mean, it's in any, with Mathematica you do it. You don't need anything very sophisticated to compute this. Okay, so in the end, what we have seen, is that the first eigenvalue in the gap of the Dirac operator perturbed by V, is the infimum over all phi's of lambda phi, where lambda phi is a number, that is given by this expression. So we have written that lambda 1 is the solution of a minimization problem. What you minimize is a functional that is not explicit. It's implicitly given by this formula. So from the mathematical point of view, life has changed because now you want to minimize something, and to minimize something, we have lots of algorithms which are stable, nice, quick, robust, whatever. Okay? From the physical point of view, this is also interesting because in the end, you are saying that the first eigenvalue in the gap that you want to identify as ground state minimizes something because a ground state should be the minimum of something. Okay? So I'm not going to, we have done things to give really, to describe a little bit more the physical meaning of this minimization problem, but I'm not going to go into that today. The only thing is that we have this very nice interpretation of the first eigenvalue and all the other ones afterwards. And this comes from the abstract theorem that you saw that looked horrible. Yes?
Is there an easy way to see non-relativistic?
Sorry?
Is there an easy way to see the non-relativistic limit?
The limit, yes, we have done all that, yeah.
And it comes out exactly.
Fine. But we do that also for the nonlinear problems, for Dirac-Coulomb, going to R3-Fock. This is quite easy to do. Yeah.
But I mean, in this expression, can one see?
In this expression, yes, you can see it, yes. I mean, not here, but you have to rescale. You have to take minus c squared. You have to. I mean, I have to go back to the units in which you have c. For example, then you take c to infinity. It's not difficult. I can show you later. Yes. Okay. So you have this nice formula, easy to implement.
How can you get chi? So you know the eigenvalue, but you don't know the eigenvalue.
I don't need chi. I can get it later because I have a formula. This supremum this is supremum problem. It's a variational problem. You can write the Euler-Lagrange equation. I mean the solution of the equation. The maximizer satisfies an equation. Once I know the phi, I know the chi by that equation. So you reconstruct the whole psi.
So is this reformulation makes the discretization problem more forgiving?
Sorry?
This reformulation makes the discretization problem more forgiving?
Yes.
Because before you said, I mean, if you arbitrarily discretize conclusions, now you can.
Yeah. Now you can. You are going to see computations here. Okay. So very quickly I say, so we have this formula, this equation that gives us the lambda phi. So in some sense we could think of this. This is a quadratic form equal to 0. You see, quadratic form in phi. So we could define an operator A of lambda phi, so the quadratic form associated to an operator, which is defined like this, so which is just this quadratic form, okay? So if we look at this operator, we depend on lambda, on the parameter lambda, because you have lambda here and here. So you consider the first eigenvalue of this operator, which is bounded below, and you call it mu1 of lambda. It depends on lambda because the operator depends on lambda, and you can see easily that A of lambda, this matrix, is monotone decreasing because lambda is here in the denominator and here it has a minus, okay? So it's decreasing. And then you can see that there is a unique lambda for which the first eigenvalue of this operator is equal to 0. Okay, this lambda, the root of this equation, the only lambda for which the first eigenvalue of this semi-bounded operator is equal to 0, that guy is the first eigenvalue of H0 plus V in the gap. So all these things have to be proved. It's not just waving my hands, okay? So, and this is very easy now to discretize, of course, because we take a basis, generated by lambda phi 1, phi n. Your favorite one, we will see later that you have to be careful about which basis you take, because it could be that if you take a basis of different kinds, you reach different infimum. There are examples like that in the literature, so you have to think a little bit about which kind of basis. I will give a result in the end about this. But in this basis, we can discretize, of course, the operator. We have now a matrix. we can look at the first eigenvalue of this matrix. We can look at the unique zero of the unique lambda for which this eigenvalue is equal to 0. And that lambda, that I call lambda 1n, is an approximation of the first eigenvalue. This is the algorithm. It's a very easy, very robust, no spurious roots, no bad surprise. Everything works fine. And you can do the same thing for all the other eigenvalues. The recipe is the same. You look at the curves, C1, C2, etc., which are the curves parameterized by lambda of the ith eigenvalue of the operator or the matrix. And for each of them, you look at the moment when you cross 0. And this will be the first eigenvalue. When the second curve crosses, is the second eigenvalue, the third eigenvalue, etc., etc. So you have an algorithm for all the eigenvalues, no surprise, no spurious root in the middle of them, perfect. They work. This works really very well. And we did some computations because we wanted to publish that in some physics journal. So we published that So we did some computations because when you publish, maybe in math you need figures, but certainly in physics or in chemistry, we learned that you need not only figures, but tables, comparison with other methods, and these kind of things. So in order to do that, we ran very easily the algorithm for atoms. It was easy. We chose to run the algorithm on very light and very and thorium, so heavy atoms and intermediate ones. We use Hermite polynomials of the splines to do it, and we also computed diatomic for diatomic molecules, a light one and a heavy one, to see if we had any problem in the computations. And things are very, the algorithm is really quick, nice, perfect. You get this is the ground state. And this is for the thorium one for Z equal 90. And we published that in PRL. And we explained the algorithm. We gave tables, we gave figures, comparisons with other algorithms, and of everything, no spurious roots, no bad surprises, no recipes. We don't need to give, because in all the existing algorithms, you have to give a recipe for the relation between the upper and the lower spinor. We don't need that, because we solve, in an algorithm, we solve it exactly or approximately for the lower part. So we don't need to impose any recipe that works or doesn't work. So this was the computations for the atomic case, and these were the computations for the molecular case, in which we looked at this light molecule and this heavy one. For both of them, the computations work very well, and so we published that in the International Journal of Quantum Chemistry some years later. Okay, so when we finished that, we were working mainly in nonlinear problems, but with that we were mostly happy, except that very quickly when we published that, some nice colleagues and friends told us there is a problem in those papers, because you are computing things, of course, it's in physics and chemistry, so no problem, but you are using this algorithm for heavy atoms or heavy molecules, for which you don't know you can apply your theorem, because in our theorem, you have your domain, you have the core, you have all these assumptions that now we are forgetting about. We got the algorithm, we compute it, perfect. But they told us you can't. It's not rigorous. You couldn't publish this, and you couldn't publish this in a math journal. In the light cases, yes, because we have information about the domains and everything, but not in the heavy cases. So we knew about that, and we knew that things worked fine, but well, we needed some years to convince ourselves to go back to the thing and try to understand and try to see try to prove that everything is perfect, rigorous, etc., etc. But we needed to discuss things about what? We needed to discuss in which basis sets we were implementing our numerical computations, because we could have different results in the algorithm depending on the base. And the second thing is, and it's related, the two questions are related, what are the domains of these operators for heavy atoms, or these Dirac operators? So maybe you were thinking, what are these mathematicians discussing about? Well, what we are discussing about is that you look, for example, at the very easy case. You take the Dirac operator and you perturb it by an exact Coulomb potential, minus nu divided by modulus of x. Well, you have to be able to define this operator as a self-adjoint operator in a good way. And it's not simple for this kind of operators. So when nu is small, when we have light atoms, let's say, when nu is less than square root of 3 divided by 2, it was known in 53, Relish proved that the domain of the operator, you can define the operator in H1. H1 is the space of functions that are square integrable and for which the first derivatives are also square integrable, okay? So Relish proved that you can define the operator fine with good properties and everything is self-adjoint in this space. But when nu is larger than this number, what? And then the next results were in the 70s, where there is a group of people in mathematical physics, Nenchu, Klaus, Wüst. They proved that for nu larger than this number and less than 1, so when you have nuclear charge up to 137, they proved that they could define the operator in some domain in a distinguished way with good properties, and they said only that the domain was between H1 and H1 half. H1 half, for non-mathematicians, is the space in which half derivatives are square integrable. In Fourier space, you can define that well, okay? So it's a space which is much larger than H1. So they just define the operator self-adjoint, but in a domain that only they said that we can do it, there is a domain, but we don't know how it is. Some years later, I mean, a number of years later, in 2008, with Michael Loss, we looked at the same problem, and we gave, we used another method to prove the existence of a self-adjoint operator, etc., and we define a little bit better the domain. We saw that the domain is the set of spinors. We saw that actually the lower spinor is in L2, is square integrable simply, but the upper one has to be in a space which is, well, for those that don't understand, just forget about this, is in the form domain of some quadratic form, okay? So we didn't really define perfectly the domain, but it was already much more information than in the previous results. And we used another method to prove this. Okay, but still, this was okay, but it was not enough to rigorously say that the computations we published in PRL were rigorous mathematically, that we had the right to do that. Okay, so much later, in 2017, we went back, we decided with Lewin and Séré, we decided to go back to this problem and clean it and finish with this. Okay, so we proved a theorem that says that you have a potential. It's not necessary, but let's look at the atomic case. Basically, you have a potential which is nuclear point potential with nu between 0 and 1, V not too positive, not too, okay? We defined a space calligraphic V, which is a little bit complicated, okay? So functions phi have to be in this space, in that space. This thing has to be square integrable, but it's explicit. And what we proved is that this space is dense in that the functions which are C infinity with compact support, very, very regular, smooth functions, are dense in V, which is important, and that this space indeed was in H1 half, like in the results of Klaus, Wüst, etc. And the main thing is that we prove that the domain, we can define the operators. The domain is given by the lower part is in L2, and the upper part is in this V. So we have something explicit about the operator. And once you have something, the domain is explicit, then you can start to see if the theorem that we applied and the algorithm that we derived from that theorem makes sense or not, okay? And so, well, this is the critical case. I will go over this. And so what we proved in the end, and this is the main thing we did in 2017, is that you take this atomic, it's not necessarily these atomic potentials, but let's just to explain our theorems, take this particular case, the Coulomb potentials. So what we prove is that, what we proved is that you take for this kind of potentials any space F, I shouldn't have called it F, but any space F, which is between C infinity with compact support, so very smooth functions, or H1 which is really a very, very large space with little regularity. You take any F there, and then you can apply the theorem to this F, and the numbers lambda k that you defined in the theorem, the min-maxes, with dependent on F, they will not depend on which particular F, and they will be the eigenvalues. So what we prove is that you can take, forget about the domains now, forget about the cause, forget about everything. You take any space of discretization. You take any base, which is either very, very, very smooth, like Gaussians, for example, or very non-smooth, like if you take, for example, finite elements that mathematicians like to take for the computations. So if your basis contains, it satisfies this thing, which is very, very large class of spaces, the lambda case will be the eigenvalues, and what is more important, the value will not depend on which F you take. You can take the min-max in this space, you take the min-max in this space, and the lambda case will be the same. This is a very robust result. It says that all these min-maxes that look complicated, etc., don't depend on the choice of basis set at all, and you can take things very, very, very regular basis sets or very, very irregular ones, singular ones, okay? So this is what we prove, and this says that the algorithm is going to work with whatever base you take finally, and you will get always a good result. And so we are very free when computing eigenvalues. Okay. So this was almost, this is what we did in 2017, and then we decided we say, well, all this we are doing for atoms. Can we do it for molecules? Of course, we knew that we could do it for molecules with a little work. And then we decided to look at the case in which you take Dirac perturbed, for example, by the sum of some Coulomb potentials in different nuclei, okay? And this is something that we could treat practically using the same methods that we had used in the previous paper. But then we said, well, it's a pity to do only this, because if we do this, we are looking at molecules in which we are considering point-like nuclei. What if we have extended nuclei, for example? Or what, more interesting, what happens if we are looking at nonlinear problems, like in Dirac-Fock problems, or relativistic Coulomb, or things like that, which are nonlinear equations, but when you are analyzing them, sometimes you have to linearize them, sometimes you have to look at some particular what you, in this community of chemists, etc., you do, that you are looking at a particle and you look at the mean field action of the other particles on that one, okay? And that, when you are doing that, you are looking at a linear problem, okay? So we said in order to take into account not only point nuclei, but taking into account more general systems with more electrons that will be described by nonlinear equations, we have to generalize these operators. So what we did was to consider not this kind of operators, but consider operators like the Dirac operator perturbed by mu convoluted 1 over modulus of x, where mu is a finite Borel measure, often positive, okay? And this covers all kinds of cases. So this, if we take this very, very general class of operators, this covers the cases in which you have extended nuclei and not point-like nuclei. It covers the case when you are looking at relativistic Coulomb or Dirac-Fock and you linearize those nonlinear equations, etc. So this is a very, very general class of operators that covers most cases that you can encounter when you are looking at molecules. Okay, so we did that. And what happens is that going from point nuclei to this general case looks like you say, well, doesn't change very much. The singularity is going to be the same. But actually, we saw that, that it was much more complicated, and you can't use at all the technology we used in the previous work. So you want to look at this class of general potentials, you need to change your methodology. And I didn't say anything about the methodology before, but just to say that this is much, much more complicated from the mathematical point of view, but we did it. So we characterize the domains, and we show the validity of the min-max characterization of the eigenvalues. As I said, this is not a simple generalization of the previous work. It's really a completely new technique to prove this. So we proved that there is a distinguished self-adjoint extension for these operators, as long as mu is a non-negative finite Borel measure that has no atom of mass larger than or equal to 1. So it can't be too singular, of course. And then all the eigenvalues in the gap minus 1, 1 of these operators are given again by the abstract min-max procedure. So we can use our algorithm again to compute in this kind of, for this kind of operators that are much, much more complicated than the ones I was showing to you before. So comments on the eigenvalues is that, well, when you have any finite Borel measure and you look at the min-maxes, okay, it's easy to see that the A minus that was in the theorem is minus 1 for Dirac. And in order to have that the lambda 1 is larger than minus 1, which was the second assumption in the theorem, you need that the measure mu is not very large, okay? So, for example, you take a fixed measure mu and you take a parameter t which is small, you will see that for t small enough, this first min-max is larger than minus 1, and then we can apply our theorem, and it will be the first eigenvalue, it will be the ground state. But if you increase t, it could be that when you increase t, for most cases, this first eigenvalue goes towards minus 1. It goes to the lower part of the gap. And when it reaches minus 1, the ground state disappears, and in some sense, the system is unstable, okay? So it's an interesting question to understand for which measures you are inside the gap, for which measures the lambda 1, the ground state exists and your system is stable. Okay, it hasn't gone into a resonance or something like that, you know? It hasn't evaporated somewhere. Okay, so one of the open questions we have is when do we have that the first min-max, I don't say eigenvalue, when the first min-max is larger than minus 1, because I know that if it's larger than minus 1, the first min-max will be an eigenvalue thanks to our theorem. But if it's less than or equal to minus 1, this min-max, you can define it, but it will not be an eigenvalue, okay? So when can we say that this happens? This is an important question for a system. How large can you take these measures? And concerning this, we have written this naturally leads to determine the critical mass, mu1, for which we have that this thing is larger than minus 1 when the mass, total mass of the measure is less than mu1, okay? So we have a theorem that characterizes this critical mass, is the best constant in a Hardy-like inequality, which is don't spend time thinking about it, but we have proved that the best constant in this inequality is this guy here, but how do you compute it? That's another problem. And using an inequality due to German mathematician Tix, we know that this constant, this optimal constant mu1, is less than 1 and larger than something that is around 0.9, so it's not far from 1. And we have a conjecture saying that the optimal mu1 is equal to 1. What we mean here is that we think that when the total mass of the measure is less than 1, the first min-max will be ground state energy, okay? But this is open problem, and we thinking about it, but it's not easy how to answer the question. Another interesting open problem in this area is the following. When you look at Dirac, and you modify it by a molecular potential, that is the sum of some Coulomb potentials, which are centered at points Rn, so you have a molecule in some sense, okay? And you model your nuclei as points, okay? So you look at the first eigenvalue of this operator. So you have an electron, you have your nuclei there, and you look at the ground state energy. It's easy to prove that when you take all the nuclei together, so you push the nuclei to a common point, for example, to the origin, all of them together, you can see that the first eigenvalue, the ground state energy, converges to the ground state energy of the same Dirac operator modified by a unique nucleus which charge the sum of these charges. Okay, so you have two nuclei, you push them together, and the ground state energy of this configuration is the same as if you push them. I mean, it goes to the limit when you push the two nuclei to the same point. Okay, and that guy, you know what is the value. But an interesting question is the following: how this limit arises?
Should this be a minus in front of the square root?
No, it's positive.
It's not a negative eigenvalue?
No, it's positive.
Okay.
It has to be less than 1, this sum, actually.
The square of the sum of the sum of the square.
No, it's because the charge here is the sum.
Yeah, but then.
Yes, sorry. So it's there is no square here, yes. Okay. It's the square of the sum, yes. Okay, so we make another conjecture, which is actually interesting, not only for mathematicians like us, is when we have this limit, do we have the limit by above or not? What I'm saying is, for an electron, what is more interesting, to see two atoms with given charges, or to give only one atom with the sum of the two charges? And so we make a conjecture that this happens, that for an atom is more economical to see only one charge and to see this charge cut into two pieces. And this is something that has been studied by some physicists. So there are results in the literature, in the physics literature, when m is equal to 2. There is a paper by McConnell and a paper by Artemiev, Indelicato told us about this result. So they have made computations and showed that when you have two atoms, it's better for a relativistic electron to have the ground state energy is optimal when you put the two charges together. Okay? So physically, they are interested in the question, and numerically, it seems that this conjecture is true. From the mathematical point of view, it's a little bit, because in the non-relativistic case, when you are looking at the case with the Schrödinger operator, the result is very well known. The fact that it's more favorable to have only one atom than several ones that cut your charge into several pieces. This is very well known, this result. And it's easy to prove because the lambda 1 in that case, in the non-relativistic case, is given by a minimization problem. And then you can use some concavity argument. There is work of Lieb, etc. about this. And this is something that is proved. This conjecture in the non-relativistic case is easy to prove. And they are even in the case of in the multi-electron case, there were several works by Lick-Simon and Obman-Ostenhoff who proved that. But in the relativistic case, we have no idea how to prove this, except in one case. Well, we could write a conjecture for general measures, not only for point nuclei, exactly the same conjecture. We think it's true, but we don't know how to prove it. Only there is a case in which we can prove it. Is the case when the measure is radially symmetric, because if the measure is radially symmetric by Newton's theorem, you have this inequality, and then since the min max is monotone in V, in the potential, then you put the two things together and you see that if the measure is radially symmetric, then the conjecture is true. But this is not very interesting for molecular case, so this radial symmetry. So the conjecture is totally open, and you can think that maybe it's a problem that interests mathematicians, but at least some physicists that we know have been interested in this and have been making computations and conjectures. The conjecture is that the conjecture is that all these inequalities are true, but we don't know how to prove that. It's a very, very, we think, serious and difficult problem to prove this conjecture. And with this, I thank you for your attention.